All right, I have attempted to switch to my other mic. Can anyone hear me? My audio mixer is showing me that I should be getting audio now. I'm very surprised. New problems every week, but we do our best. I'm going to be very sad if I've just been talking into the void here for a little bit, but if I need to, I will go back and re record this. Still nothing. Can you hear me now? This is, I think, the last change I'm going to try, and then we're going to move. We're going to move on. Fantastic. Okay. Ah, thank you. So it appears that in my audio mixer there were two options for my headset mic, and one of them was a red herring. So I apologize for that. If I need to go back and re-record the first couple of problems on this, I will. So right now we are looking at periodic trends again. We have a sort of abbreviated periodic table here. Looking at electronegativity, the trend is increasing electronegativity as we go up and to the right. So from its position on the periodic table, determine which atom in each pair is more electronegative. So first up we have bromine. We have bromine versus chlorine. Chlorine is higher up on the periodic table than is bromine, and so for this one, chlorine would be our more electronegative atom. Next up we have phosphorus or sulfur. Sulfur being a little bit more to the right on the periodic table, we can say that sulfur is more electronegative. Thank you guys so much in the chat for alerting me to the issue. Really, really appreciate it. And finally, nitrogen or potassium. So we have nitrogen and potassium. Nitrogen is both higher up and further to the right than is potassium, so that is our more electronegative atom. All right, which atoms can bond to sulfur so as to produce a positive partial charge? A positive 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 partial charge. Say that 10 times fast on your sulfur atom. So the key here, remember that to have a polar covalent bond, we need to have a electronegativity difference of 0.4 to 1.8. So we have a fantastic comment here in the chat, and I think this was talking about electronegativity trends. You are correct. So noble gases are not considered electronegative, are not electronegative because their valence electron shells are full. They have 8 valence electrons, which is the state that all atoms would like to be in. And so they don't really want to give up their electrons. They also don't want to take anybody else's electrons. They're happy the way that they are. And so that final group right here, which is removed, is not included on this chart. So that was a really great observation. Yeah. And you'll also notice that hydrogen is up here in the top left, and it has kind of a unique value of 2.1. Hydrogen has some unique properties too, because it really only has the one proton and one electron to do anything with. So those properties are really important. It's why we have things like water, which is, as we know, very important for life on Earth, which we may have another opportunity to talk about. All right, so atoms that can bond with sulfur. Let's take a look at sulfur. Sulfur has an electronegativity value of 2.5. So we're starting with 2.5. and we need minus x. I'm going to write this as an algebraic formula, um, where your answer is going to be a range of zero point 0.4 to 1.8. Make sense? So let's try carbon, for example. So 2.5 minus 2.5 is 0 if we're looking at carbon and sulfur. So wouldn't be carbon. Let's try nitrogen. 2.5 minus 3, you have a difference of 0.5, which falls in that range. So nitrogen would work. Put this over on the right here. We can do, we know phosphorus won't likely, actually it might. Yeah, so nitrogen, yes. Let's do -1. We've got oxygen, so oxygen works. 2.1 for phosphorus would give us a difference of 0.4, so phosphorus would work. That's in our threshold. And we're looking at just nonmetals because sulfur with any other metal would be an ionic bond, as we talked about in those earlier trends. Let's see. So nitrogen, oxygen, phosphorus, um, fluorine would work. Would probably, well, it could bond with itself, but that would be nonpolar. And chlorine would also work since it has the same value as nitrogen. And I think, you know what? I'm going to say phosphorus probably won't work, actually, because it was exactly 0.4. Ah, I know why that won't work. If we paired sulfur with phosphorus, sulfur is more electronegative by quite a bit than phosphorus, and for that reason, the sulfur would have a partial negative charge, so del negative. You'll see this this annotation later in your chemistry career, but that's just a good thing to be aware of. Because the sulfur is more electronegative, even though the difference is greater than is in that threshold of zero point 0.4 to, what did I say, 1.8? Yes. Um, it would be a polar covalent bond, but it would not have a positive partial charge, which was part of this question. And so for that reason, phosphorus would not be included. So we've got nitrogen, oxygen, ooh, fluorine, and chlorine. And I think that's it. So NOFCl. Okay. Question 21. Identify the more polar bond in each of the following pairs of bonds. So in looking at these, we've got hydrogen fluoride and hydrogen chloride. So the hydrogen remains the same. We just have to determine which one, fluorine or chlorine, has a greater electronegativity difference relative to hydrogen. Let me get rid of some unnecessary pen strokes here. So hydrogen with its value of 2.1, we're comparing to chlorine and fluorine. Fluorine is quite a bit more electronegative than chlorine. So fluorine. Hydrogen fluoride has the more polar bond. Next up, we have a bond between phosphorus and chlorine, or sulfur and chlorine. Phosphorus and chlorine, or sulfur and chlorine. Right away, we can tell just by proximity on the periodic table, the difference between sulfur and chlorine is much less than phosphorus and chlorine. Not by a whole lot, but a little bit. So phosphorus and chlorine is our answer. Next up, we have CN, which would be cyanide, or dinitrogen. Excuse me, that's not cyanide. That would be, well, okay, it doesn't. It would be cyanide. Um, I have to chase this down now. Cyanide would be a anion of carbon and nitrogen, or bonded to a hydrogen, hydrogen cyanide, which is not at all relevant to what you guys are working on right now. So I apologize for the departure, but I was too curious not to check. Okay, I digress. So the difference between CN or NN. This one we don't even need to look at the periodic table. Nitrogen and nitrogen would have an electronegativity difference of 0, and so CN, carbon and nitrogen, is our more polar bond. All right, so Lewis, oh my goodness, Lewis symbols and structure. I love that somebody brought up noble gases in the chat because um, if we have a noble gas like argon, argon is already super happy with its 8 valence electrons. It does not want to give any of them up. It doesn't want to take on any more. It's perfectly comfortable in the energy state that it's in. And this would be its Lewis structure right here. We're showing all 8 of those valence electrons. Now, when we're looking at ions, negative charge implies that we have additional electrons added to the valence shell, and a positive charge, a cation, indicates that we have removed valence electrons. And so as a convention here, when we draw these, I'll just do the example and then explain. So for AS, we have arsenic, and boy, I really want this to be in the background and not move around. Thank you. We have arsenic, and arsenic is 1, 2, 3 positions to the left on the periodic table from our noble gases. And so from that, we know that it would normally have 8, 7, 6, 5 valence electrons. Arsenic would normally have 1, 2, 3, 4, 5 valence electrons. Now, this has a 3 negative charge. And so we're going to add 1, 2, 3 valence electrons, giving this an overall 3 negative charge. So to redraw this in the same color, 1, 2, 3, 4, 5, 6, 7, 8, because we have our 5 plus 3. Yep. Brackets, and then 3 negative. So that is how you would write this arsenic ion with the 3 negative charge. Next up, let's look at gallium. Gallium is a metal, and gallium with a 3 positive charge does not have any valence electrons. You normally have 3, basically. We don't have to change anything because the 3 valence electrons that it would otherwise have are gone. And so that's our complete answer. For nitrogen, stand by. Nitrogen normally has five valence electrons. When you're drawing these, it's also good to be in the habit of drawing one on each side, if we're imagining a box. Fill in all four slots, and then if you have additional valence electrons to work with, then start pairing them up. So nitrogen normally has those five. Is that right? 765, yes. And then we're adding 3 to give it that 3 negative charge. And so again, we have nitrogen with its full valence shell and a 3 negative charge. Cool. Okay, write the Lewis symbols of the ions in each of the following ionic compounds and the Lewis symbols of the atom for which they are formed. The atom for which they are formed. Okay, so let's look at the individual species first. We have magnesium and we have sulfur. And on our periodic table, we have magnesium and sulfur. Sulfur normally has 8, 7, 6 valence electrons. Magnesium normally has 2. We can look at this and infer that 6 plus 2 makes 8. For that reason, they're going to want to share these. But not share, exchange. They're going to want to exchange electrons. Actually, I think I want to color code this. So magnesium's blue electrons over here are going to jump ship and join up with sulfur. And so you will get magnesium with a 2 positive charge. The sulfur has taken those 2 electrons and achieved a 2 negative charge. For the Lewis symbols, let's see. Let me make sure I've got this right. Yeah. Let's actually check the answer key for this one and triple check that this is the answer they want. Yes. Yeah, okay. So similar story with potassium and oxygen. For potassium, we've got 2 of these. Okay, I'm just going to write it once. Looking at our periodic table here. Potassium's got 1. Oxygen has 6. So potassium, each of those potassiums is going to give up their electron. And the oxygen yes. Oxygen would normally have 6, picks up 2 from each of the potassiums, and oxygen achieves that 2 negative charge. Okay. Question 28. Write the Lewis structures for the following. All of these are going to be covalent bonds. We were looking at ionic bonds a moment ago, and now we're looking at covalent bonds. So we have a question in the chat. So a Lewis symbol uses only the dots while a structure adds the bond lines. I may have inappropriately been using these interchangeably. I apologize if that's the case. I don't know, to be honest, if that's the convention. Um, I think, yeah, I think that a Lewis structure implies bonding relationships between multiple species, and a Lewis symbol would just be the individual species by itself. Maybe. Write Lewis structures for the following versus write the Lewis symbols. Yeah, it must be. You are 100% correct. So the ionic behaviors that we just did are not, they don't behave the same as covalent bonds, and so we notate them differently. These are the, yes, these are the Lewis symbols for the individual ions that emerge when these species interact. By contrast, if we have two hydrogens, each with their lonely electrons, those are going to want to team up. And so you will see this Lewis structure drawn a couple of ways. This is one, where you have the two dots stacked between them, which communicates that they're sharing those electrons. The other way that you'll see this drawn is simply with a line between them. So each line, this is really important, each line conveys that there are two electrons. So there's your hydrogen. Oh, come on. So now we have hydrogen with its one electron, and bromine, which is in that one group over from the noble gases, has 7. And those two electrons are going to share. So for hydrogen bromide, you get again, I'm going to draw this in red as I'm counting them out. There's 1, 2, 3, 4, 5, 6, 7, 8 electrons. It may be important to do some accounting here. So when you look at hydrogen and note that it has one electron and one valence electron, and bromine and note that it has 7 electrons, the sum is 8 electrons. So you can check your work at the end here and go, are all of my electrons accounted for? 1, 2, 3, 4, 5, 6, 7, 8. Yes, all of my electrons, all of my valence electrons are accounted for. Hope that helps. All right, let's take a look at nitrogen. Normally has 5. I'm going to put that over here. And oxygen normally has 6. 1, 2, 3, 4, 5, 6. But we have a negative charge on here. So one of these is going to end up with an extra electron. So let's go ahead and do our accounting here. So we've got 5 electrons plus 6 valence electrons plus 1 extra electron gives us 12 total electrons. Okay. So when we bond our nitrogen and our oxygen, we can go ahead and throw one bond in between them. That's, let me think here for a second. 2, 3, 4, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5. How do I want to explain this? This would not be the correct answer, by the way. Mm, okay. Yeah, I do like this explanation actually. So we've got our 12 electrons. If we subtract a single bond, that's 2 electrons. So if we have a single bond between the nitrogen and the oxygen, then 2 of those electrons are now accounted for. Gives us 10 left over. That's still more than can comfortably fit around those atoms. So let's subtract another 2. Yeah, I think I like that. Subtract another 2, account for another 2 of those electrons, gives us 8 left over. Do I like that? Almost. Group those together and apply our negative charge. That is your correct answer. So again, there's now 8 electrons in the valence shell occupying the, excuse me, there are now 8 electrons occupying the valence shells of each of the species. All of our electrons are accounted for. All of our electrons are accounted for. None of these species are hypervalent, which is a thing you don't have to worry about yet. And our charge is accounted for. So that is our answer. Cool. All right, we've got one left. We have carbon and nitrogen. And we have a negative charge. So 4 plus 5 plus 1 equals 10. Yeah. So you will come to recognize this one, hopefully, pretty readily. And I'm just going to give you the answer here and make sure that I account for that last electron. Yeah. So here we have 2, 4, 6 accounted for. There's room for 2 more electrons around each of these species in their valence shells. And that has a negative charge. So that is your answer. Okay. Last exercise. We have more than two, more than 2 species now in these bonding patterns. And what's important to know about chlorine is that it can accept, it can handle having more than 8 electrons hanging out around it. So it's also important to know that in these Lewis structures that the atom that is listed first is usually in the center. And when we draw these 3 other fluorines around it, you want to space them out evenly. And this is working towards getting what is a more true representation of how these molecules are arranged in space. And so for this, Chlorine normally has, yeah, chlorine normally has 7 valence electrons. Fluorine normally has 7 valence electrons. What we're going to do here is we're just going to draw a line between these. There's 6 already accounted for. And each of these fluorines, through covalent bonding, already has 2 electrons accounted for. We put the other 6 around them. And now let's do our accounting. So we would have chlorine has its 7 plus 3 times each of fluorines, which is 20. Is that right? Second guessing myself here. Yes. Yes. Okay. Gives us 28 electrons total. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. We're missing some electrons. We're missing 4 electrons. And this is where I mentioned earlier, it's important to know that chlorine can handle having more than 8 hanging out around it. And so we would put the remaining 4 electrons around chlorine. Right? I'm going to not rely on my fingers for counting this. Where is my calculator? Yeah. Yep. 28 total. Minus 6 is 22. Minus 3 times 6 is 18. Is 4. Yep. Okay. This is why we show our work. Sanity check. Okay. Chlorine trifluoride. Next up, we have phosphorus and fluorine. 6 fluorines with a negative charge. This is this is wild. So let's look at our periodic table. Excuse me, phosphorus. I said fluorine, didn't I? That is fluorine. P is phosphorus. 7, 6, 5. Gives us 5 electrons. 6 times 7 is 42. Gives us 47 total yes, plus 1, because we have that negative charge. Gives us 48. 48 total electrons. It is important to know that phosphorus can handle having all of these electrons around it. 1, 2, 3, 4, 5, 6. Just got to know that. So 2, 4, 6, 8, 10, 12 are accounted for through bonding. So we have 36 left. And each of those fluorines has started with 7 valence electrons. 1 from each is accounted for in the bonding. And so we need to subtract 6 times the remaining 6 electrons is 36, is 0. Now, when you get to a certain level of chemistry, you will be expected to know this and be able to, you'll be expected to intuit that those additional 6 electrons are there. And so when you see this drawn, it will simply be drawn like so. And a negative charge will be there. Make sure you can see that. That's future. That's future chemistry. All right, question in the chat. If I remember from lecture, period 3 and higher can handle more than 8 valence electrons because they can open their lower s and p orbitals. That sounds correct. I want to make sure that I tell you exactly. So I'm going to pull up the textbook. Molecular structure and polarity. Let's see. Excuse me. Predicting electron pair geometry and molecular structure. That's not exactly what we're talking about. Here we go. Yeah, I don't think that. Period 3. Period 3 would imply all of that. That's not necessarily true. What is it? I know where I can check. My notes from when I took the class. Because if it was in lecture, it would be included in the lecture slides, and I definitely have those. What do you mean you can't sign in right now? Okay. Let me think about this for a second. 221, chapter 7. You're about to take a peek inside my brain here. Ionic bonding, covalent bonding, Lewis symbols and structure. Exceptions to octet rule. Hypervalent molecules have central atoms with more than 8 valence electrons, or expanded octets. This is only possible for elements in row 3 or above of the periodic table. The extra valence electrons are stored in empty d orbitals. Row 3. Period 3. Does above mean higher number or higher up on the periodic table? Since chlorine is in period 3, that would make sense. Bromine is period 3. Yeah, you're 100% right. It's period 3 and higher in number. above his higher in period number. Thank you so much for checking me on this because frankly, it's been a while since I've looked at this material and I don't have to deal with hypervalent atoms terribly often. Um, they do come up and it is important to understand this concept, especially once you get into like stranger inorganic compounds. Yeah, that's what I'm reading into from this lecture slide, which should be exactly what you guys have. Only possible for elements in row 3 or above of the periodic table. The extra valence electrons are stored in empty d orbitals. Elements in row 2 do not have d orbitals, and so there's nowhere for them to go. Most expanded octets contain 10 or 12 electrons. 14 is possible, but is less common. I have written here in red, which usually for me when I was studying meant that this was emphasized by the professor and was likely to be on an exam. We won't know a valence, we won't know a molecule is hypervalent until we draw the Lewis structure and distribute the valence electrons. The fact that there's so much red on this slide suggests that it might actually be very important for you to know. That's all I have for you this evening. Thanks for sticking around. Um, while I'm here, actually, since it sounds like, well, my audio was cut off for the first part of the video, but you can tell pretty much. I think this was the simplest part of the worksheet, and if you understood the rest of it, that this should be pretty clear. I also wrote down all of the important bits. Yeah, we wrote down all of the important bits. We came in talking about electronegativity, and I was talking about the kind of subjective differences in these values. This is what's in your textbook. This is what it should be in lecture. Um, you should know those, I think, for the exam and be able to calculate electronegativity difference and know if it is a polar or a nonpolar um, covalent bond. I will say my recollection is the professor was pretty good about making it very, very obvious. The difference was going to be like greater than one or infinitesimally small, right? Just know that a very small or no electronegativity difference means that it is nonpolar. That means even distribution of charge between those bonded pairs and or bonded atoms. And polar is going to have some difference, not more than 1.8. So ionic bonding is a complete transfer of electrons. And so each of those species will have a charge associated with it. Anyways, I hope this is helpful. That's all I have for you. Have a great weekend. I won't see you next week live. I'm going to be recording something over the weekend. I may live cast it, but because I'm not scheduling it, I'm not going to advertise a specific time yet because I also have things I need to do. But next week's will not be live. There will be a recording on YouTube posted, I'll say by Monday, by end of day Monday. So look for that. Have a great weekend. Enjoy your holiday. I'll see you all in a couple weeks.